Hello everyone. Today we are going to analyze this frame using flexibility matrix method. Before analyzing, let us see the frame one time. In this frame, there are two columns, column AB and column DC, and there is a beam BC. This frame is symmetrical in the dimensions. Also, the loading is symmetrical. So, this is a non-sway type frame. The columns carry point loads 20 kN in the centers. The beam carries uniformly distributed load 15 kN per meter acting for the full span. The length of the columns is 4 meter and the length of the beam is 5 meter. The moment of inertia for the columns is given as 2I and for the beam it is I. In this frame, we can easily find the vertical reactions in the points A and D because we have symmetrical loading. In this frame, there is only one vertical load 15 kN per meter. It is acting for the full span. To convert this UDL into point load, we have to multiply this 15 with the distance 5. When we do that, we will get the total load. To get RA and RD, we have to divide this total vertical load by 2. Finally, for RA and RD, we are getting 37.5 kilonewton. Now let us find the degree of static indeterminacy. In this frame, the number of unknown reactions and moments are 4. In the points A and D, we have fixed supports. In the fixed supports, there will be horizontal reaction, vertical reaction, and a moment. We have already found the vertical reactions. In the point A, still we have to find the horizontal reaction HA and the moment MA. In the point D also, we have to find HD and MD. So the number of unknown reactions and moments are 4. The available equilibrium equations are 2. Sigma m is 0 and sigma h is 0. The degree of static indeterminacy is equal to 4 minus 2. We will get 2. To make this frame statically determinate, let us remove the moment MD and the horizontal reaction HD. You can see that from the point D, I have removed MD and HD. This structure is called the released structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates HD and MD because we have removed both of them. Let us assume that HD is acting towards right hand direction and MD is acting in the clockwise direction. Finally, if we get positive values, that means our assumption is correct. If we get negative values, that means our assumption is incorrect. We know the formula to find out the final reactions. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Delta matrix is the flexibility matrix. The size of the flexibility matrix will be 2 cross 2 because in this analysis there are two coordinates. Inside the phi matrix, we will have the final answers HD and MD. Inside the delta L and delta matrices, we will have two values because in this analysis there are two coordinates. In the given frame, there is no overhanging or settlement of the supports. So inside the delta matrix, we can simply enter 0, 0. So in this formula, only we have to find delta matrix and delta L matrix. To make these matrices, we have to make sections. Let us keep this point as F and keep this point as E. In this frame, there are 5 different parts: AF, FB, BC, CE, and ED. So we have to make 5 sections: one in AF, one in BF, one in BC, one in EC, and one in DE. You can see that I have made 5 sections. Then we have to find the moments in these sections. Since the frame and the loading is symmetrical, the moments in the sections 4 and 2 will be same. Also, the moments in the section 5 and 1 will be same. So, no need to consider these two sections. We can only find the moments in the sections 1 and 2 and multiply the integrations by 2. Now let us make the free body diagram. Let us split the frame in the point C. You can see that I have split the frame from the point C. Now I have two different parts. In the point D, there is a vertical reaction 37.5 kN. For the equilibrium condition, for this upward reaction, in the point C, a downward reaction is created. In the point E, there is a horizontal load 20 kN. To counter this load, a horizontal reaction is developed in the point C. This load is acting towards left side, so the reaction should be acting towards the right side. Now let us find the moment in the point C. This 20 kN is acting towards the point C in the clockwise direction and the distance is 2. 2 into 20 we will get 40. Since this load is acting in the clockwise direction, the moment in the point C should be acting in the anti-clockwise direction. Now let us take the left side. On the right side in the point C, vertical reaction is acting downwards. So here the vertical reaction should be upwards. Here the horizontal reaction is acting towards the right side. So here it should be acting towards the left side. Here the movement is acting in the anti-clockwise direction. So here it should be acting in the clockwise direction. The sections should be made at the distance of x. The first section is made at the distance of x from the point D. The second section is made at the distance of x from the point D. The third section is made at the distance of x from the point C. Now let us take this part and find out the moments. We know that the moments in the portion DE and AF will be same. Also the moments in the portions EC and FB will be same. We are going to find the moments towards left hand side. So clockwise will be negative and anti-clockwise will be positive. Now let us take the portion DE. Here the moment of inertia is 2I, so the flexural rigidity will be 2EI. The origin is in the point D. The limit is 0 to 2. Now let us find the moment in the section. Up to the section, there is only one force, that is the vertical reaction. For this vertical reaction, there is no perpendicular distance, so the moment will be 0. Now let us take the portion EC. Here the moment of inertia is 2I, so the flexural rigidity is 2EI. The origin of the section is D. The limit is 2 to 4. Now let us find the moment in this section. For this vertical reaction, there is no perpendicular distance. This horizontal load is acting towards the section in the clockwise direction, so it will be negative. For the distance, we have to take this distance. This distance is x minus 2. Let us multiply minus 20 with x minus 2. When we do that, we will get this. Now let us take the portion CB. Here the moment of inertia is I. So the flexural rigidity is EI. The origin is in the point C. The limits is 0 to 5. Now let us find the moment about this section. For this 20 kilonewton, there is no perpendicular distance. This movement is acting in the clockwise direction, so it will be negative. The UDL 15 kilonewton per meter is acting towards the section in the clockwise direction, so it is also negative. The distance is x. For the UDL, we have to multiply the distance and distance by 2. This 37.5 kilonewton is acting in the anti-clockwise direction, so it will be positive and the distance is x. X into x, we will get x square. 15 upon 2, we will get 7.5. In this analysis, there are two coordinates. First, we have to apply unit load in the first coordinate and find the moments. Then we have to apply unit moment in the second coordinate and find out the moments in the sections. Now let us apply unit load in the first coordinate. When we do that, we should not consider other reactions and the loads. You can see that in the first coordinate, I have applied unit load. Before finding the moments, let us make the free body diagram. We have applied unit load in the point D in the coordinate direction. It is acting towards right hand side. So in the point C, the unit load should be acting towards the left hand side. This unit load is acting towards the point C in the anti-clockwise direction. The distance is 4. 1 into 4, we will get 4. So the moment developed in the point C should be 4. Since this load is acting in the anti-clockwise direction, the moment developed in the point C should be acting in the clockwise direction. Now let us take the left side. Here the load is acting towards the left side. So here it should be acting towards the right side. Here the movement is acting in the clockwise direction. So here it should be acting in the anti-clockwise direction. Now let us take this part and find out the moments. Previously, using the given loads, we found the moments. There we kept the moment as m. Here let us keep the moment as m1. Let us take the first section. This load is acting towards the section in the anticlockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us take the second section. This load is acting towards the section in the anticlockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find the moment in the third section. For this load, there is no perpendicular distance. This moment is acting in the anticlockwise direction, so it will be positive. Now let us apply unit moment in the second coordinate. You can see that I have applied unit moment in the second coordinate. Now let us make the free body diagram. In the point D, we have applied unit movement in the coordinate direction, that is the clockwise direction. So in the point C, the unit movement should be acting in the anti-clockwise direction. Now let us take the left side. Here the unit movement is acting in the anti-clockwise direction. So here it should be acting in the clockwise direction. Now let us take this part and find out the moments. Let us name the moment as M2. Let us take the first section. Up to the section there is no load. We have only the unit movement. The unit movement is acting in the clockwise direction, so it will be negative. Let us take the second section. Up to the section there is no load, only the unit movement which is acting in the clockwise direction, so it will be negative. Now let us take the third section. This movement is acting in the clockwise direction, so it will be negative. We have calculated the movements in all of the sections. In this formula, now we are going to find out delta L matrix. In delta L matrix, now let us find delta 1L. The formula is integration of capital M small m1 upon EI dx. For DE and AF, the moment M is 0. The moment small m1 is x. 0 into x, we will get 0. For EC and FB, caps M is minus 20x plus 40. Small m1 is x. Since there are two members, we have to multiply the integration with 2. The flexural rigidity is 2EI and the limits are 2 to 4. For CB, caps M is minus 40 minus 7.5x square plus 37.5x. M1 is 4. The flexural rigidity is EI. The limits are 0 to 5. Now, using the calculator, we can make integration. If we do manually, it will take more time. If you do not know how to make integration in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator. Using the calculator, for this integration, I got this. And for this integration, I got this. After adding these two values, I am getting minus 925 upon 3EI. Now let us find delta 2L. The formula is integration of caps M small m2 upon EI dx. Let us apply these values in the formula and these two values in the formula. Finally, after the calculations, we are getting delta 2L, which is equal to 83.75 upon EI. In the delta L matrix, we have found both of the values. Let us apply them. 1 upon EI is constant. Let us keep it outside. In this formula, now let us find the delta matrix. First, let us find delta 1, 1. The formula to find out delta 1, 1 is integration of m1 square upon EI dx. In this formula, let us apply the values. For DE and AF, M1 is X, let us apply that. For EC and FB, M1 is X, let us apply that. For CB, M1 is 4, let us apply that. After the calculations, we are getting delta 1, 1. Now, in the delta matrix, let us find delta 1, 2 and delta 2, 1. Both of them will be same. So, to calculate both of them, we have same formula. In this formula, let us apply the values. In this integration, let us apply these. And in this integration, let us apply these. And finally, in this integration, let us apply these. After the calculations, we are getting minus 28 upon EI. Now, in the delta matrix, let us find delta 2, 2. The formula to calculate delta 2, 2 is integration of m2 square upon EI dx. Let us apply the values. In this integration, let us apply these. In this integration, let us apply these. And finally, in this integration, let us apply these. After the calculations, we are getting delta 2, 2, which is equal to 9 upon EI. In the delta matrix, we have found all the values. Let us apply them. 1 upon EI is constant. Let us keep it outside. In this formula, we have found everything. Let us apply them. 1 upon EI inverse is EI. We can add these two matrices. After adding, we are getting this. Then we can eliminate EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find the inverse of a 2 by 2 matrix, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we can multiply these two matrices. After multiplying, we are getting the final values. For HD, we are getting 3.36 kilonewton. For MD, we are getting 1.14 kilonewton meter. Both of the values are positive. That means our assumption is correct. Now let us find HA. Let us assume that it is acting towards left hand side. Now let us apply the rule sigma h is 0 and find out HA. For HA we got a positive value. That means our assumption is correct. Now let us take moment about A and find out MA. Let us assume that MA is acting in the anticlockwise direction. When we take moment, no need to consider these two loads because this is acting in the anti-clockwise direction and this is acting in the clockwise direction. Both of them will get eliminated, so no need to consider them. Finally, after the calculations, we are getting MA. For MA, we got a positive value. That means our assumption is correct. Now, let us take AB and make the free body diagram. Let us apply the rule sigma h is 0 and find out HB. Then let us take moment about B. In this way, we can find out MB. For BA, MB is acting in the clockwise direction. So for BC, it should be acting in the anti-clockwise direction. In the similar way, we can make the free body diagrams. Now, using the horizontal loads, let us make the shear force diagram in AB. Now, using the vertical loads, let us make shear force diagram in BC. Now, using the horizontal loads, let us make the shear force diagram in CD. We can draw the bending moment diagram by superposition method. In this method, first let us make the free movement diagram. For that, we have to assume every span as a separate simply supported beam. Using the formulas, we can find out the moment values. Then, using the direction of the movements, we can make the end movement diagram. Now, let us combine the end movement diagram and the free movement diagram so that we will get the bending moment diagram. Now, we are going to end this session. Thank you for watching this video.